So our next speaker is Gemma Crowe from Heriot-Watt, who will be talking about conjugacy, languages, and groups.
Thank you very much, Alan, for the invitation to speak today. And a thank you as well to all the organisers for organising World of Groupcraft #3. I think it's a really unique and great seminar to have over 24 hours. And I'm glad to see that it's still carrying on despite the pandemic somewhat being over. So hopefully, long may it continue. So my talk today, I want to talk a bit about some of the work I've done so far in my PhD and my most recent paper, which is in a world of geometric group theory that is perhaps slightly less well known and perhaps a bit more obscure, in that I want to talk a bit today about formal languages. But as it turns out, these actually come up in a variety of different ways in group theory, and these can actually be quite an interesting tool to use. So my talk today is very much a tale of two halves. The first half, I need to tell you the formal language theory side of things, because I appreciate not everyone here has perhaps seen formal languages, and that's absolutely fine. We're not going to do anything terribly complicated today. It's all going to be fairly basic stuff. And then the second half, we'll go back to the group theory side, and we're going to try and see how these two things are interlinked. And I'll be focusing later on right-angled Artin groups, and I might mention a bit about graph products if I've got some time. But yes, as I was saying, the point of today's talk, I guess, is to try and highlight that amongst these three very broad areas in geometric group theory, that there definitely is a non-trivial intersection between all three. So groups and growth, you've perhaps seen before. Well, I hope you've seen groups before. And you've probably seen the intersection between those two, but formal languages tends to originate from the world of computer science. So that perhaps seems a little bit more obscure amongst all this group theory stuff. So, okay, I'm saying there's a non-trivial intersection, but let me give some more motivation and evidence that there really is. So going back to the 80s, Cannon was looking at hyperbolic groups and geodesics in hyperbolic groups. So, you know, this is a very geometric property of groups, but they went on to show that when you consider these as a formal language, they form a regular language, which I'll explain what that is in a little bit. Not only that, but actually, due to recent results, we can actually completely categorize when a group is hyperbolic based on looking at quasi-geodesics and looking at them from a formal language perspective. And if, depending on whether they're regular or not, that will tell you when a group is hyperbolic. So it does very much capture a geometric property of a group. Now, one word in my title that I haven't mentioned yet is the word conjugacy, and that's a particular property that I'm interested in studying. So where this partly began, probably the main paper is this 4-author paper in 2016, where they created languages which represented conjugacy classes, essentially, and studied a wide variety of groups and looked at different properties of these languages. So in a very hand-wavy sense, which will hopefully become clearer by the end of the talk, the plan for today is to try and describe which conjugacy language properties, whatever I mean by conjugacy language, but hopefully that will become clear, which of these properties are preserved under quasi-isometries. So one thing I'm very interested in is looking at finite index subgroups. And in particular, if I have, say, a group G sitting as finite index in a group H, if G has some property, as if in the conjugacy language, if that has some property, does that somehow correlate through the quasi-isometry to the bigger group H? We don't know yet. So I need to tell you what I even mean by a conjugacy language, and in fact, what I even mean by a language in that aspect. So this is the formal language part of the talk that I need to go through. So languages themselves are very easy to define. First of all, you need a finite set, and I'll let x star denote the set of all finite words over some set x. You can think of x as like an alphabet in a sense. So for example, I could take x to just be 0, 1. So x star just gives me the set of all binary words. So that's fairly straightforward. Now a language with no conditions, nothing on the side in a sense. It's simply just some subset of X star, whatever your X is. Okay, so the most common type of language that, well, more common types of language that we all know. For example, you could take the English alphabet and you'd have the English language. Of course, depending on wherever you are from in the world, whatever your native language is, that also is a perfectly valid language in this world that we're talking about. And that's really it. That's as simple as a language can get, essentially. So now what we want to do is somehow categorize different types of languages. And okay, we're going to be working with infinite languages, but they have different characteristics in a sense. And the way this has been categorized is through something called the Chomsky Hierarchy. Now, I'm not claiming there are other types of languages out there. This is, I guess, the most common set that you have in this hierarchy. And I actually won't be looking at the top two, as in context sensitive and recursively enumerable, because they're way too scary and we're not going to focus on them. So we're really only going to focus on regular and context-free languages for today. Now, how you define these types of languages, there's lots of equivalent ways of defining regular and context-free languages. And if you've seen formal language theory before, you've maybe seen, for example, finite state automata are used to define, say, regular and context-free. For today's purposes, I'm going to stick with definitions using something called grammars, purely just to make things a little bit easier and to keep things in kind of one type of definition. But like I say, these definitions are all equivalent. So if you've seen a finite state automata definition, it's the same idea that we're going to go through. Okay, so grammars themselves are simply just a mechanism of generating languages. So formally speaking, we need a for tuple, which consists of some variables, some terminals, some relations, and in particular, a start symbol from your set of variables. So out of the relations, one thing I do require is I'm mapping a word u to a word v, which is taken from the intersection of variables and terminals. But the crucial thing is my word u can't just consist of terminal letters. So it has to must have some variable letters in there as well. Now, this definition on its own, well, I personally think is a bit abstract. It's a bit difficult to visualize what's going on. But grammars themselves, when you're just working with them, are very straightforward. So let me just talk you through an example if you've not seen these before. So this grammar that I have, we've got 4 rules. My start symbol is the symbol s to make things straightforward. And I also have another variable a. And my terminals are just the numbers 0, 1. So what's going to happen is I'm going to write words over 0 and 1. Okay. So how does this work in practice? How do we generate words? Well, for example, I could create the word 0001 by starting at s and simply just picking this sequence of rules. Hopefully it's clear as to I take the first rule, for example, to get me to 0s, and then I take the first rule again, etc., etc. So you're just choosing different rules to get you to different words. And so the question then is, okay, out of all possible combinations of correct rules that you could use, what are all the words that you can produce as a language? And if I gave you like 5-10 minutes to think about it, you would realize that if you consider all possible words which are generated by this grammar, it's simply all words which are a sequence of zeros and a sequence of ones, and that's it. You don't have any particular restrictions in terms of this L and K, the only thing being that you have at least 1 0 and at least 1 1 in that list, and that is you. So this is the language generated by this grammar. So let me go back a sec to the Chomsky hierarchy, because I want to be able to define what I mean by a regular language and what I mean by a context-free language using grammars. So let's start off with regular, first of all. So our grammar is regular if each of your relations is one of the following 3 forms. So it's quite restrictive in a sense. It has to be one of these 3 forms. The epsilon here just means the empty word in this sense. So going back to the grammar I had previously, if I just bring up the relations, you can see that each of these falls into the types of relations we need for a regular grammar, right? You can just kind of check them off one by one. And so this language generated by this grammar is in fact a regular language. It's kind of the classic example of a regular language that you can have. Okay, cool. So that's one of the two done. Context-free, a grammar is context-free if for any of the relations, the starting word that you, on the left-hand side of the relation, is of word length 1. Now, by these definitions, you can see that any regular language is necessarily context-free, and that came from the Chomsky hierarchy as well. But there is examples of languages which are context-free but not regular. And one example of these that I want to highlight is actually a language that all of us mathematicians use every single day when we're using LaTeX, for example. So one thing that you may find when you're writing up with LaTeX is when you're putting any brackets. If you close off brackets properly, LaTeX is fine. But if you don't, if you leave somehow unbalanced parentheses, it starts to, flash in red and it gets a bit unhappy, which is never good, right? So we can consider this all possible balanced parentheses as a language. So how does this work in practice? Well, what I could do is I can create a grammar which will produce all balanced parentheses as words. I should say here, I'm just restricting to say one type of bracket, but you could extend it to as many different types of brackets as you like. That's absolutely fine. But just to keep it simple, I'm doing one type of bracket. And the reason I'm emphasizing this grammar is if we go back a second to the regular grammar, you can see that this balanced parentheses grammar doesn't fit into this category because you've got, for example, the second relation is of length 3. So it definitely doesn't fit that. And if you want to test out whether this really produces balanced parentheses, I mean, this is by no means a proof that it does, but proof by example, just to highlight this producing an example of a balanced parentheses. But I think it's fairly clear you can see how that will work in terms of generating all possible balanced parentheses. Okay, so that's regular and context-free languages sorted. I actually have one more type of language that I need to define, which I didn't mention before, but I'm just going to sneak in at the end. So suppose you have a context-free grammar. We say that it's unambiguous context-free, or UCF, which is a lot shorter to say, if the grammar produces each word in a unique way. Okay, so you have a unique root of relations that gets you to every word. So to give an example, rather than give an example of a UCF grammar, I'm going to give an example of an ambiguous context-free grammar, just to highlight the opposite way. So here I have start symbol S again, and I'm mapping towards over A plus and star. And I mean, this is by no means just the only example, but here we have two different ways that we can get to the word A plus A star A by using the different production rules. So this is an ambiguous context-free grammar. So really now the Chomsky hierarchy that perhaps I should have started with that we care about goes from regular to UCF to context-free, one sitting inside the other. And in terms of the formal language theory that you need to know, that's essentially it for this talk. We've kind of done that part of the talk. So now I can start to move back into the world of groups and in particular the world of growth as well and see how this all ties into things. So thinking first about growth rather than groups, first of all, because this is, I guess, one of the more defining links between all of these different areas. So suppose I give you a language. It doesn't matter if it's regular or whatever. I can define a counting function, which literally just counts the number of words you have in that language of length n, and that's you. And then from that, it's very natural to just then create an infinite series, which just counts the number of words of length n, etc. Right? So for example, if you were doing growth of groups, you're counting elements of length n, sort of thing. Now, based on the type of language you have, that can tell you stuff about the series that you've constructed. So, for example, if your language is regular, your series is rational, meaning that you can write it as a fraction of polynomials. It may be absolutely hideous, the fraction, but you can write it like as a fraction. If your language is UCF, the series is algebraic, meaning it's some root of a polynomial. And taking the contrapositive of that, if your series is transcendental, then your language cannot be UCF and therefore cannot be regular by the Chomsky hierarchy. So I guess the takeaway from this is if your language is nice, your series is nice. If your series is bad, the language is bad. And unfortunately, these directions don't always go the other way. But I guess the point I'm trying to make is if you're wanting to understand something about the series, what can help is understanding something about the language first, and that might give you implications as to what the series might be, or maybe can't be as well. Okay, so I've talked about languages, I've kind of talked about growth. We need to get back to group theory at some point. So let's see how we can put all of this together. And indeed bring back conjugacy as well, because I haven't really spoken about that yet. So now imagine we have a finitely generated group with a generating set X. And pi here is just simply your natural projection from words to group elements. Now the next bit is very notation heavy, but I promise there's examples coming. So if it's a bit much for the notation, that's fine, don't worry. So we want to be able to create some sort of language which encapsulates conjugacy in some way. So first of all, I'm going to define G bar for any group element G to be the length of a shortest representative word. So you can think of geodesics, right? And then for any conjugacy class, I'm going to create a similar kind of length definition, which is a minimal length up to conjugacy in that conjugacy class. So the first language we can create, which talks about conjugacy in a group, is what we call the conjugacy geodesic language, okay? And this is simply all words over your generating set where the word length is precisely the minimal length up to conjugacy when you project to the relevant group element. Bottom line, basically, which of the words are shortest with respect to their conjugacy class, and that's you. So let me give an example just to give you an idea what these languages might look like. So let's say we have the free group and we take a generating set of just A, B free generators. So one can show that the conjugacy geodesics are precisely the set of cyclically reduced words, which if you haven't heard of that, that's simply all words which cannot look like U inverse VU. Okay, and the reason they can't look like that is if I give an example, if we say had the word A inverse BBA, right? If we conjugate W by A, we end up with a word that is of length 2, which is shorter than W, which is of length 4. And so the word BB will be a conjugacy geodesic, because now that's cyclically reduced, but the word W will not be part of this language, okay? It is a geodesic because it's freely reduced, but it will not be a conjugacy geodesic in that language. Okay, the second language I want to describe will lead us more into growth and counting things again. But to do that, I need to put a bit more consideration into the generating set that I have. So for any generating set, we can assign some sort of ordering on our set. So I've given an example here, again, staying with A and B. And when we talk about short lex, what we mean is we first order by lengths of words, but then we also order by reading left to right and depending on the order of your set X. So here, for example, the second letter on the left is A and on the right is B inverse. And because A is less than B inverse with respect to that ordering on X, then we have that ordering on those words. So imagine for every conjugacy class, I now want to take the short lex least word which represents an element of a conjugacy class. And then from that, I simply just take all possible ZCs that I have. And we call this language the short lex conjugacy language from that. Again, if that's a lot of notation or weird stuff, just think you have a unique representative for every conjugacy class. So you're taking out one representative for each one. And this language is particularly interesting because since we have a unique representative for every conjugacy class, what we can build from this is what's called the conjugacy growth series. So if you've seen growth series before, it's the exact same idea, but now we're counting conjugacy classes, okay? And this series, compared to growth, is still somewhat mysterious. We still don't know a lot about conjugacy growth in a lot of groups. But using the ideas from before, depending on the nature of this language, might tell us something about the conjugacy growth series. So that's part of the motivation behind looking at this type of language. Okay, so now that I'm getting nearer towards the end of time, I should talk about some stuff I've done, because this is all stuff really arguably I've not done. And the groups that I've been focusing on so far in my PhD have been right-angled Artin groups. So right-angled Artin groups, hopefully everyone has seen these, but if you haven't, you just need a finite simple graph, and the generators are your vertices of your graph, and the relations are simply two generators commute if and only if there's an edge. Sometimes in the literature it's the other way around, but you know, it's all equivalent, it's all fine. And I guess if you haven't heard of RAGs before, the reason they're so interesting is that they describe a spectrum from free groups to free abelian groups. So free groups being graphs with no edges, so no generators can commute. Or on the other end, if you have a complete graph, then every generator can commute and you have the free abelian group. And there's a lot of, it's very much a hot topic at the moment, you know, and the classic thing is to try and anytime you have a problem which you can solve in free and free abelian groups, you try and solve it in RAGs, and it gets a whole lot more difficult. But that's what makes it interesting as well. So let me just recap from the beginning what we were trying to even do in all of this. So I'm interested in RAGs, and in particular when I have a RAG as a finite index subgroup of a group G, and I wanted to study what conjugacy properties in languages were preserved from, say, a RAG up to the bigger group G. And so I constructed these languages of conjugacy geodesics and ConjSL, and then we try and study what's going on with those languages and see if anything, if this can tell us anything about what's going on. So to highlight a few results, well, most of which are not mine, but this gives you some examples of some other groups, and in particular, you know, a lot of geometric properties as well, and other virtual groups, because I was looking at virtual RAGs. So the results that were mine, ConjSL I managed to show for both RAGs and in a lot of cases of these virtual RAGs are not context-free. So yeah, quite bad. Often ConjSL is either not regular or not context-free sort of thing. So in that sense, that language did kind of preserve the same properties through the quasi-isometry. It stayed not context-free. But then the question is, for conjugacy geodesics, what happens? So for right-angled Artin groups themselves, we already knew these were regular. This by Ciobanu and Hermiller in 2013. So then my question was, well, do virtual RAGs stay regular? Do conjugacy geodesics stay regular? And the punchline, in a way, is sometimes they do, sometimes they don't. So I managed to find some cases where a virtual RAG could be regular conjugacy geodesics, but then I also found another example where it was not context-free. So very much not regular, so quite different. So I guess the bottom line in all of this is quasi-isometries definitely don't guarantee the same types of languages. There's lots of weird and wonderful stuff, I guess, going on. So to finish off, I'll just provide a couple of references. In a weird way, I'm not going to recommend my paper first of all. I'm going to recommend the 4-author paper in 2016, only because if you've not seen this stuff before and this has piqued your interest, go and read that one first, because that's where a lot of this stuff is first defined, and they look at, you know, a whole bunch of different groups. So my paper more focuses on, well, generally graph products, but mainly right-angled Artin groups and right-angled Coxeter groups. And, you know, you might be interested in other groups, which I appreciate. So, you know, go and do that first. But ultimately, one thing with this project is I think I've ended up with more questions than answers after writing this paper. So if anyone wants to have a look and see if they want to find out more about some of these questions or give them a try, I'd love to hear from you as well. But on that note, I think I'll just finish up there. So thank you.
Okay, does anyone have any questions for Gemma?
So I have a question.
Sure.
So you've used a short lexicographical order. Would it make sense to look at different orders in some cases? In the case where the group is orderable, of course.
So I haven't so much thought about when the group is orderable, but one thing I will just mention is if I go back to that slide actually with the ordering, yeah. The ordering on the choice of the generic set, first of all, and indeed the ordering can affect what type of language you have. So for the generating set, first of all, there were examples of virtually Abelian groups where if you change the generating set, this language became regular or not regular. The other very weird thing that I found in my paper was, so the way I proved these results was I defined something called a twisted Conj-SL language, which is basically to do with twisted conjugacy. And what I found was if I changed the ordering on the generating set, again, I had similar weird results of it could be regular or not regular, depending on the ordering I had on the generating set. So yeah, it can be quite different, and that's why you have to define what generating set and indeed what ordering you're talking about, because it can vary.
I see. Thank you.
Are there any other questions? So I was wondering if this can ever tell you anything about decidability of the conjugacy process.
So I don't know of anything, but one thing that was mentioned in the 4-author paper was if you consider the conjugacy geodesic language, it's somewhat an open question, I guess, whether regularity of that language implies decidability of the conjugacy problem, but it's still, we don't know.
Okay. And there's no way, the other question is, are you able to classify groups in terms of languages? Like groups of polynomial growth or virtually nilpotent?
Oh, I see.
Or is there any vision to prove anything like that?
I mean, there is a vision in the sense that going back to the beginning, there's this result of classifying hyperbolic groups by quasi-geodesics. But I guess, like, polynomial growth and all the rest of it, not that I can think of off the top of my head. But I guess maybe more difficult. I mean, that result on hyperbolic groups was only just last year, the other direction. So,
Okay, great. Thank you.